Hello everyone. Now I'm going to talk about problem 1 for homework 10. Actually, this is a summary for the notes of the professor. From the lecture notes, collect the definitions and simple properties of examples of stochastic processes. First, the Poisson process. This is we should start from the definition of it. The number of incidents happened in a certain time period. For example, the number of calls received in time T2 to T1 follows the Poisson distributed random variable. For Poisson process xt, we define x0 equals 0 and consider the number of incidents happened in the time interval T2 to T1, and the lambda is the average rate. For we know that the probability that the number of incidents happened in time t equals k is e minus lambda t power k is, and it is xt1 minus xt2 equals k. This probability is e minus lambda t1 minus t2 lambda t1 minus t2 k. This, and the mean value is lambda t. This is a linear function of t which is reasonable because the longer time we wait, the expected number of incidents happen is larger. And the autocorrelation is lambda square t1, t2 plus lambda times the minimum value of t1 and t2. Okay, so for the second part, we consider the Poisson increments. With xt, a Poisson process defined above, and epsilon larger than 0, a given constant, we construct yt equals xt plus epsilon minus xt over epsilon. The distribution density should be these things. And n is the number of calls in t to t plus epsilon. So the mean value is lambda. In a very small period, the expected number of incidents is fixed and is related to the average rate. And if we consider the autocorrelation, we should consider whether the time interval t1 to t2 is outside the range of epsilon. So there are two possibilities. First is lambda square. Second is lambda square plus lambda over epsilon minus lambda, absolute value of t1 minus t2 epsilon square. Larger than or equal to epsilon, less than epsilon. Third, Poisson impulses. We define Zt equals d over dt xt, which means that the epsilon is very close to 0 for xt. So the mean square should be lambda because it is very similar to the Poisson increments. And the autocorrelation is lambda square plus lambda delta t1 minus t2. Fourth, semi-random telegraph signal. With xt, a Poisson process, and pk here. We define x0 equals 1, and the stochastic process is defined as xt equals 1 or minus 1 for k is even or odd in the time interval 0 to t. So the probability masses are E minus lambda t cosine h lambda t. And similarly, the mean value is E power O minus 2 lambda t. As time goes, the expected number is closer and closer to 0. And the autocorrelation is now for the fifth part. The random telegraph signal. Let alpha be a random variable independent of xt with probability of alpha equals y equals to the probability of alpha equals to minus 1 equals to half. And we consider yt equals alpha times xt. So this means that we have equal probabilities for xt to be positive or negative. And now the probability of xt equals 1 should be this, and xt equals to minus should be this. The expectation of alpha is exactly 0, so the mean value is 0. For the autocorrelation, it is just the same as this one. 6. Random walk. Consider an experiment of tossing a fair coin for infinite times. During n times of experiments, there are k times of head and n minus k times of tails. Xt equals to x, nt equals to 2k minus n times s for nt less than or equal to t less than n plus 1t. At t equals to IT, we define a random variable yi equals to s or minus s if it is hit, if the coin is head, or minus s if the coin is tail. The probability masses should be probability of 2k minus n equals r, which is this. And we now have to consider the exact situation for the probability of x and t less than or equal to rs. Finally, it is approximately half plus ERF r over square n. The mean value is 0 as well. However, we have to note that this value is Rs. That is, the mean of all coin flips approaches 0 as the number of flips increases. Also, the diffusion is ineffective for mixing because of the way the square root behaves for large n. And the autocorrelation is the minimum of n and m times s squared. 7. The winner process. We define it as a limiting process of random walk. The conditions are t to 0, n to infinity, and s squared over t to alpha. The second moment is defined finite and non-zero, while the expectation of w squared t is alpha t, where alpha is a constant. The density is listed as follows. We consider this, it is half plus ERF, and the function is, the probability function is this. Similarly, the mean value is 0, and the autocorrelation is alpha times the minimum value between T1 and T2. That's all for this problem. Thank you for your listening.